The overall process that we're going to follow here with the hypothesis test and coming up with some sort of statement of significance is going to be really a two-step type of process in the big picture. We're going to assume that nothing unusual, nothing hinky is going on. That is, that our whatever process that we have is operating in some sort of normal expected fashion, that the only variation that's happening is a natural variation. And then we're going to ask the question of how likely is it that the given result that we obtain occurred by chance. This is a fundamentally different kind of question than we asked with confidence intervals, which was to have a specific procedure by which, say, 95% confidence, we would then come up with an interval for, say, the true mean. Whereas here we're saying we're going to instead do something like conduct a test, calculate a sample mean, and then make some hypothesis and ultimately ask the question of, given the sample mean we just calculated, how likely was that to have happened? And that's a crucially different kind of thing, even though we're going to end up using pretty much the same distribution models that we were using before. Along the way here, this notion of that we're going to assume that nothing unusual is going on leads us to coming up with what we call the null hypothesis, usually given the symbol H naught, or 0 for the null. And again, that is all about nothing going on. Machine has not gone off calibration in the assembly process. Our basic ingredients that we're using, say, in the production of a material have not become somehow flawed or of a different kind of quality or pulled from a different population. By nothing going on, we mean that all variation that we see is just the natural inherent variation in the process. Okay? And if there's a null hypothesis, of course, then there is some sort of alternative hypothesis that usually has one of two symbols, either H sub 1 because people look at this as a 0 and the other one then therefore must be 1, or they'll use the symbol of A for alternate, with the suggestion then that something is going on, that the piece of equipment has gone out of calibration, or what have you, or maybe the moisture content of the aggregate in your concrete is actually significantly different than what you anticipated. Right, so defining these two are crucial, and we'll get into what we call type 1 and type 2 errors and rejection operation rules and those sorts of things as we go along. But first, let's ask some general questions on the way to a couple of examples of setting up the hypothesis, because ultimately what we're trying to do with these two is, in particular the null hypothesis, is to ask the question of, is there convincing evidence? And by is there convincing evidence, partly what we're saying is give this data to anybody and they would develop the same conclusions. Rather than being purely subjective, we're trying to move this evidence into the objective world. Right? And so oftentimes this can be answered by measuring by probability, but ultimately because of using standardized variates and certain approaches, we could actually also talk about this in terms of quantiles, 10th percentile, that sort of thing. We could also talk about it in terms of number of standard deviations away from the mean. Right, there's a lot of ways that ultimately it comes back to this kind of notion of probability. In application, you might not state it by probability, but maybe one of these other sort of terms. Okay. Along the way, we have to create operating rules. And I'm going to differentiate slightly between what some people will call decision rules versus operating rules. Decision, in my world, tends to include risk or the consequence of something happening. Operating rules may not. They're just simply a rule without regard to the consequence of a yay or nay, reject or no reject. Whereas the decision will oftentimes then, of course, include the implications of that. Okay. One thing that we have to keep in mind here is that as we address this question of is there convincing evidence, is that we need to couch our conclusions carefully. Right, we can rule in something, but not necessarily rule out, or it might be the other way around, depending on what you mean by these two things. But the basic notion is that it can be very easy to demonstrate that something has happened, that something is possible, but not necessarily to do the reverse. So you can easily demonstrate, more easily demonstrate that someone is guilty than it is to demonstrate or prove that someone is innocent. Sort of very difficult to prove a negative type of thing, so to speak. Let's get this more in engineering terms. And as an example, let's talk about, say, concrete with a design value for the compressive strength of 4,000 psi. Now, we won't get into the subtle and different meanings of different kinds of design value for the concrete. Let's just take this as 4,000 psi, which happens to be, by the way, one of the most common your normal garden variety structural concrete that's around. And we've then observed tests, say, of 4,010, 3880, 3970, 3780, and one more, 3820 psi, where our sample mean of those be 3892 psi, a little bit lower than the 4,000. And sample standard deviation here is 97.3 psi. So our desired or our assumed design value of 4,000 psi turns out to have when we went and made this, the sample mean is about 1 standard deviation away from that. Is that significant, or is it not? Does that represent just natural variation in the process, or is there something else at work here that, for instance, the concrete actually is not quite strong enough? So our null hypothesis might be then that our true mean for the concrete was 4,000 psi, and our alternative hypothesis might be that our true mean was less than 4,000 psi. Right, so here maybe we're if we decide to reject this hypothesis, then we're saying, hey, this concrete is less than, the tests show that it's less than, and now it's a pretty strong statement to the this is now a pretty strong statement that now the manufacturer is going to have to potentially do some work to demonstrate, well, no, actually this was just by chance, and they then go and attempt to demonstrate that no, really they do have strong enough concrete. Another way to do this would have been to say, well, mu is greater than 4,000 psi as your alternative hypothesis, in which case there it's maybe you have a good strong track record for this particular kind of concrete, and so maybe you feel that there's a weaker kind of thing that you're allowing to do. Now, there's always the possibility we could make an error in accepting or rejecting one of these, and that's exactly what type 1 and type 2 errors are about that we'll get into later. And there's one more way that we might have done this, and that would have been to say mu is just simply not equal to 4,000 psi. These top two are examples of one-sided significance tests or hypotheses, and the bottom one is going to ultimately be a two-sided. We're probably in this particular context, because of the things that are of interest to us, and that is weak concrete, then we're probably going to use a one-sided one in practice as compared to a two-sided for this particular kind of application. All right, let's take a look at another example of building a set of hypotheses, and that is from a potato chip manufacturing process, where it's been found over time that the ideal salt content has about a 6.9% ratio, and it's known that the variation of salt content is 2.7% for the standard deviation. And we've now come along and we pulled 5 samples measure their salt content, and we get a sample mean that's equal to 8.2%. And so, of course, the natural question then that someone might want to ask is, has the process changed? In other words, is this significant? Or do we just have natural variation at work? So here the hypothesis test might be, or the null hypothesis might be, that our true mean is 6.9, and now in this kind of quality control situation we don't really care if it's high or low, as in we care in both, I guess, in a sense, is what I'm really trying to say, that it's not just one-sided we're interested in. It doesn't matter which side, it's either side that's not good for us. Right? If we get concrete that's stronger than what we had set as a target, that's okay, but if we get concrete that's then less than what we had set, well, that's not good. Here, either side is the not good. And one of the real challenges here is to recognize is that if we come back and we had a sample mean of 6.8, wouldn't that be okay? What about 6.7? What about a little further away? How far away does this have to get before that starts to be not acceptable anymore? And what's the likelihood, and all those sorts of things get into what we call operating rules. So let's get into this potato chip example a little bit further here. And let's go back to what we know about things such as the expected value of x bar, our sample mean, is going to be equal to the population measure itself, right? So mu of x bar is equal to the population measure itself, as opposed to the variance of x bar is going to be equal to the variance of the population divided by n. And of course that just means sigma, standard deviation, is equal of x bar is equal to sigma divided by square root of n. Right? In our first case, that's equal to 6.9. In the second case, that's going to be our 2.7 divided by square root of 5. Right, and that is 1.207-ish. Okay, so question still becomes, well, what do we do with this? We came up and we had an observed sample which gave a mean of 8.2, and that of course is 1.3 away from the mean, just a little bit more than one standard deviation, which should already tell us something, right? Because there's no reason to think of this as anything other than coming from a normal population, and as soon as you think normal, then you should think about z, right? And that becomes our test statistic. Z equaling to x bar minus its mean divided by its standard deviation. And in this case, we've got 8.2 minus 6.9 divided by sigma over square root of n, which was 1.207, and that's going to equal 1.08. Right, notice there was that 1.3 I was talking about, 1.3 divided by 1.207. That z is really number of standard deviations away from the mean. Hence why I said we could measure our evidence by probability, or we could measure it by quantiles or number of standard deviations away from the mean, and that's partly where we're headed here, just to draw that out. Right? And remember that in the normal population, that if you are plus or minus one standard deviation, that captures something like what, 68-ish% of the population within those. It's kind of an interesting thing to kind of keep running around in your head. So let's ask the question more directly here. There's two different kinds of questions we might ask. One is, well, what's the probability in a two-sided kind of situation here that our sample mean would have been between 8.2 and 5.6? And in this particular case, I chose 8.2 specifically because that's what we observed. I chose two-sided because I don't really care if it's high or low. Both of them are not good, and so what's the chance that x bar might be between that, in that region? Right, now there's other cases where you might want to do this as a one-sided kind of thing, so don't get too stewed up about my somewhat arbitrary choice here. Right, and on a z level, then this is then probability that z is between plus and minus 1.08. Right? And from a calculation standpoint, we can do this a variety of different ways. But the way I've posed this, I'm asking the question of the central area. And since we're given in tables the cumulative sitting way out here, and so it would be all this area to the right of the upper minus the area here on the left. Oh, that's just that tail kind of area. We could do this and write this in a variety of different ways. One of them is to actually do this as 1 minus 2 times this tail area. Right, so here's this z that's the lower value, minus 1.08. There's your z tail area. We've got 2 of those, subtract it all from 1 would be one way to have done this. And look that up, you get 1 minus 2 times 0.14. There's, of course, more numbers sitting out there, and that equals 0.72. So 72% chance that our x bar would be in that central region. More commonly, what you actually are going to calculate is not that, but rather, well, what's the probability that x bar was less than 5.6, or x bar would be greater than 8.2. Right, that's directly that tail area. In that case, that's going to be our 28% chance. And that's pretty large. Right? That says 1 out of 4 times we'd expect x bar to be maybe hanging out way out in there when we're only sampling with 5. That's a key thing here. We've only done a sample size of 5. Right? If we did instead a sample size of 10, this might change things here. Well, not might. It would. It would change things. Right? This number here that we get, this lower one, the tail area, is our p-value. Right? That's the probability of contradictory evidence for our null hypothesis. Remember, our null hypothesis was that G mu is equal to 6.9, right? And we have a 28% chance that mu is equal to 6.9, and yet we ended up with a sample mean that was 8.2, right, which was 1.08 standard deviations away. If we instead had an x bar that was 9.2, then we're going to have much smaller tail area, right? The z value will kick up quite significantly. Right? And when we get into control charts later in the semester, we'll actually start talking about plus and minus 3 sigma. And remember, that has about 99.7% of the area. So if we start seeing things outside of that, well, that's a pretty rare type of event, which is what we're really kind of interested in, that when things get out there like that in those extremes, then that turns out to be kind of significant to us. Right, so this p-value is what we call our observed significance level, and will get reported quite a lot. Now, that doesn't tell us whether it's acceptable or not. That's an operating rule, and that's something else that we'll come up with here in just a moment. Small p-values give evidence to reject our null hypothesis. Right? If this had been 2.8% chance, a less than 3% chance that we would have seen a sample mean of 8.2 when the true mean was 6.9, suggests that the true mean is not really 6.9, and that instead we'll go to the null hypothesis. Okay? Whereas large p-values And this is a critical thing, critical statement about what we conclude. It doesn't say for sure that the alternative hypothesis is correct. It just says large p-values fail to give evidence to reject HO. Right, so this is kind of weird, right? So the first one, small p-values, if this had been, say, 2.8% or something like that, well, gee, then that gives us fairly strong evidence that we ought to reject HO and then correspondingly accept the alternative hypothesis. Whereas large p-values fail to give evidence to reject HO. In this case, this is a fairly large kind of p-value. Right? And what does raise the question of, well, how do you know what the operating rules should be? And some of this goes back to the same kind of thing that we were dealing with confidence intervals, and that is, what do we do by convention? And that the statements that we're providing are really a statement of, well, how did we come about doing this? Not so much anything else. Right, so these conventional p-values are on the order of 10, 5, 1%. And we'll say things such as that the results are statistically significant at whatever that p-level or p-value turns out to be. Now these are, when I say conventional p-values, these are now the acceptance values. And we'll get into more discussion of that later, especially when we get into talking about type 1 and type 2 errors. Right? These values that you have there are really sensitive to risk. So if you're talking about a cancer drug and its effectiveness, then you might want to have this at a much smaller kind of level. If you're talking about salt on a potato chip, then maybe 10% works real well. The value that I see most commonly running around in my work is the 5 and the 1 percentile level, but 5 being perhaps the most common. So before we go off into more interpretations and developing this in deeper, one last set of things that we really need to go back to and hammer in on is the importance of setting up the hypotheses. Those hypothesis statements are all important. And note that they have to be about, they're always about a population parameter. And so that would be things like mu, variance or standard deviation, or maybe proportion, or some such things like that, right? And then we use a test statistic that is appropriate to what we have there. So we might be looking at using X bar, or we might be looking at the sample variance, and commonly what we're really going to be looking at is Z equaling X bar minus its mean over its standard deviation, or we might be looking at the t distribution, where now we've substituted in sample standard deviation for the population. Right, and remember, this is just sigma over square root of n. And likewise, when we start looking at things associated with the population variance, then we start looking at the chi-square distribution. So in that sense, it's very similar to the way that we approached confidence intervals, and you'll see the same kind of pattern. Things coming from a normal distribution with the variance known, and then what do we do if variance isn't known? Well, is it large sample size? Is it small sample size? And then hypothesis test is on the mean, and then or on the variance, and then we'll get into in another module we'll get into multiple samples. So now we'll look at differences of means and that sort of thing.